In this session, we study basics of how to detect and handle nonlinear relationships in linear regression. This session has two major learning objectives. First, we study what nonlinearity means in the context of linear regression. Then, we learn basic methods for working with nonlinearities in linear regression analysis. In this session, we start with the concept and detection of a nonlinear relationship between an independent variable x and the dependent variable y. Then we will learn about two widely used procedures for handling nonlinearities: conversion of x to an ordinary scale, and polynomial regression. After that, we discuss some related issues as appendices. Let's look at the basic model of linear regression. When we use linear regression, we assume that the independent variables and the dependent variable are related as expressed by this model, which is an equation of a very simple form. For example, there is no x squared, square root of x, log x, or e to the x power. Let x sub j be the jth independent variable. It may be a numerical variable or a binary variable, but let's suppose x sub j is a numerical variable. If x sub j is related to y, it may be a good idea to include x sub j in the model, but their relationship, controlling for the other x's in the model, may not be linear. This model implies the change in the outcome, y, corresponding to a unit change in x sub j is always the same, b sub j, controlling for the other x's. If we draw a curve representing this relationship, the slope of the curve is always the same, which is what b sub j represents. In a linear model, the relationship between y and x sub j is linear. A linear relationship means that the relationship looks like a straight line. There are many nonlinear relationships in the real world. This graph shows death rates by age for U.S. women, in the period between the years 2000 to 2004. This graph indicates that the death rate increases with adult age in an accelerated way, not linearly. Mathematically, a linear relationship between x and y means that an increment in y, corresponding to a unit increment in x, is constant. The pattern in this graph indicates that among adults, the increasing death rate corresponding to 1 year increase in age is not constant. The increment is relatively small in middle age, but becomes larger and larger with an advancing age. The majority, or probably most, of laws discovered in natural sciences such as physics and chemistry indicate nonlinear relations. The basic method of detecting a nonlinear relationship is to plot data points on a two-dimensional plane with horizontal and vertical axes, as in the previous slide. If the plot looks very messy, some techniques such as local averaging and smoothing help to capture the overall pattern. This is a plot of systolic blood pressure by age, in a subset of NHANES data. The points are scattered, but the center of vertical dispersion may appear to move upwards, from left to right. This is a plot of BMI by age in the subset of NHANES data. Points are widely scattered, and it is difficult to detect a systematic trend. To capture the overall pattern of scattered points, local averaging was done. Each circle represents the mean systolic blood pressure for a 5-year age group interval. The leftmost circle indicates that the mean systolic blood pressure of those aged 20 to 24 was around 110. And the rightmost circle indicates that the mean systolic blood pressure of those ages 80 to 84 was close to 150. This pattern seems to show that systolic blood pressure tends to increase with age at fairly linear rate. This is the same type of graph for BMI. It looks messier than the graph for systolic blood pressure, but we may be able to fit a bell-shaped curve, an inverse U-shaped curve, to the points. It does not seem appropriate to fit a straight line. If we find a nonlinear relationship, then how should we work with it? We may still be able to use the linear regression analysis, after some conversion of x or y. If the nonlinear relationship is complicated and it is difficult to find an appropriate conversion, we may adopt an approach called nonlinear regression, which deals with more mathematically complicated forms than the linear one. Methods based on multidimensional smoothing, and methods that allow changes in parameter values, may also be used. Let's study variable conversions with examples, which include regression of systolic blood pressure and regression of BMI. The independent variables are race, ethnicity, education, and age. The dataset included only female respondents. First, a numerical independent variable may be converted to an ordinal scale variable. An ordinal scale variable is a categorical variable whose categories can be ordered in a logically meaningful way. Suppose we have age as a continuous numerical variable, ranging from 20 to 84. This variable can be converted into 5-year age groups, 20 to 24, 25 to 29, and so on, up to 80 to 84. Now we have age as a set of 13 categories, and this categorical variable is an ordinal scale, because the age groups can be ordered from youngest to oldest, or from oldest to youngest. Age as an ordinal scale was included in the regression model of systolic blood pressure, and that of BMI, as a set of 12 binary variables, not including the youngest age group 20 to 24, which was selected as the reference category. The other independent variables were gender and education. This is a plot of partial regression coefficients for the age groups. The vertical axis is the value of regression coefficient, and the horizontal axis is numerical age. The data point for a 5-year age group is placed at the center of the 5-year age range. 0 is assigned as the value of partial regression coefficient for the reference category, which covers ages 20 to 24. This graph suggests that systolic blood pressure is fairly linear when related to age, so the use of age as the original numerical variable seems reasonable. This pattern of regression coefficients looks quite similar to that of local averages. This pattern was adjusted for race, ethnicity, and education, but the pattern of local averages was not. Nevertheless, the two patterns look quite alike, probably because age was not very strongly associated with race, ethnicity, or education. This is the same type of plot for BMI. It looks messy, but the points may also look scattered around a bell-shaped curve, i.e., an inverse U-shaped curve.